There we go. Now we're broadcasting. Anne, if you'd like to start.
Okay. Hi, everyone. This is Anne Reed, Director of the National Center for Science Education, with the next session in our course about handling controversy in the classroom. And this week's session is on how science works and some of the misconceptions that people often have about it that can sneak into your classroom sometimes without your even being aware of it. So we're going to draw your attention to some of these misconceptions so that you can be sure to prevent them from continuing in your students' minds or getting reinforced in your students' minds as you teach science. The first thing that I want to do is let you know how you can interact with us. If you want to ask a question, there are several ways you can do it. At the left-hand side of your screen, there's a question and answer app that if you see it already, you can go ahead and use. You may have to add it or enable it. If you don't, you can tweet to @NCSETeach, or you can email Minda at berbecco@ncsc.com. She'll be watching for your questions, and she'll let us know when questions arrive. The second thing that I want to do is introduce the other teacher for this session, Stephanie Keep. Stephanie wears a lot of hats at NCSE. She's the editor of our new quarterly report, and she's an expert on evolution and on misconceptions about evolution. She's an expert editor and communicator about how to teach evolution. So she will be stepping in after another couple of slides. You've already had two sessions, one about why certain areas of science are controversial, and then one about how to bring authentic language into your classroom. And as I said, this week we're going to talk about specific misconceptions about science. And the two key questions are, what is science and how does it work? Which may sound simple, but it turns out people have a lot of different ideas about what the answer to those questions are. So before we go on, does anybody have any questions from the reading that we and the resources that we posted before the session, or about any of the previous sessions? Minda, do you see anything?
Nope. I realized I had to unmute. Yes. Hold on a second, Andy. I'm getting some. I just got a little bit of feedback from you, so I muted you for a second there. So we do have one first question. So the question that came in was, the lesson I follow from my textbook talks about the linear scientific method. I don't really have time to change up that rushed lesson. Any resources I can use to get me started?
Yeah, it's an awesome question. Hold it for like 10 minutes. The short answer is yes. The long answer is to come.
Okay, great. We'll come back to that then. 1 second, and I'll unmute Anne. Okay, you should be unmuted now.
Okay, I'll let you get back and make sure that.
So Anne, you should be unmuted now.
Okay, can you hear me now? Yes, no? I think you still can't.
Yes, you're good. We can hear you.
All right, so what's our purpose in asking these very big, seemingly obvious questions? The reason is that we want all of your students to realize as they take their science classes through their middle and high school years that taking a scientific approach, thinking like a scientist, are things that they can do and should do in their daily lives, that we can all approach problems and questions in a way that we learn in science class. It's a skill like all of the other kinds of skills that you learn in school. It's a lot more than just memorizing a list of facts or learning how to apply a set of equations to word problems. So we want that main message to come through, and it often doesn't because of these misconceptions about what science is and how it works. They may so students may come to think that science is something that they don't or can't understand, or that they're not good at, or that is something that only a few special people can do and they cannot. If they're in that, if they come out of science with that very negative attitude, or that very alienated attitude to science, then they're going to be much more vulnerable to being misled by the arguments of people who are trying to confuse them about scientific matters. And they're really going to miss an opportunity to use a really great critical thinking skill that can come from science. So I now would like to introduce Stephanie again, because she's going to lead you through some of the first misconceptions that people have about science and scientists. Stephanie?
Thank you. So before we jump right into the misconceptions, just to help illustrate this point that Anne was making about this really, to our eyes, dangerous us versus them mentality that can come up with science, that science is something that other people do, whereas I don't do science. And you hear this all the time. Students will say they're not a science person, or or there's a question that was asked in a national survey to name a scientist, and 70% of the people that answered said they can't. And of the people that said they could, most of them said Stephen Hawking, because a film about him had just come out. So that's terrible in our eyes. First of all, they all know scientists. Of course they do. They know their science teachers, and I'm sure that they know other professional scientists. And I think it's important that we try to break down this idea that science is something that happens over there, or that only happens within the walls of a science classroom. And to illustrate that, I wanted you to think about how your students, what would they draw? If you walked in on the first day of class and you said, draw a scientist. What does a scientist look like? What would they draw? And chances are pretty good, even though I don't know your students. I do know of teachers who have done this before, and people have written about this, that you get a lot of kind of old white dudes in lab coats. And so here we've got our sort of quintessential mad scientist. But this is a lot of students' idea of what a scientist looks like. And I have a personal pet peeve about all scientists do something with beakers of colored liquid, but that's a little bit beside the point. But the fact is that this is what students think of when they think of scientists, and that shouldn't be the case. Like I said, they know their science teacher, and chances are good they know a lot of other scientists. So really what we want students to think of is we want them to think about themselves. If Anne, you can go to the next slide. These people are all scientists. Science happens in lots of different ways. It doesn't all happen in the lab. It certainly doesn't involve a lab coat all the time. And it's done by people of all backgrounds, both men, women, people of color. People are out in the field. People are in a lab. It happens all over. And the danger in thinking that this isn't true, if you don't have this perception, if you think of the mad scientist, that's a really one-dimensional view of what a scientist looks like, and studies have shown that you're much more likely to trust someone that you can identify with. And if you can't identify with a scientist, then chances are much better that you won't trust science and you won't trust a scientist. This is one of the main reasons that NCSE has rolled out this program, Scientists in the Classroom, to bring in actual real scientists from your community to come into your classroom. But again, as science teachers, I also encourage you to introduce yourself to your students as a scientist and a teacher. but we can also bring in other scientists in the classroom to help students see themselves in these people who are all doing this wonderful science all over. So another little exercise would be to ask your students, what does the scientific method look like? And you've all seen this diagram, and the chances are actually fairly good that this diagram is in your textbook. It is the scientific method. You ask a question, you do research, usually in a lab with colored liquid and a lab coat. You form a hypothesis, you do an experiment, again, lab coat. You get some data, you come to a conclusion, you revise if necessary, and repeat. That is so boring, and luckily, that's not how science works. There really is no one scientific method. And this diagram comes from the wonderful website Understanding Science. This is what your assignment was all from, to go and explore this site. And this is what science looks like. And this is simplified, by the way. It meanders. It turns back on itself. It takes weird turns. It doesn't always involve experimentation. It can involve observation. It doesn't always involve coming up with a hypothesis first. Sometimes the hypothesis hits you over the head somewhere in the middle, and then you got to turn back and go again. Inspiration comes from all over the place. It just is not a linear process. And what's important is that if you need to get rid of this one-dimensional view of how science works, because if you don't, first of all, that's boring, and second of all, you can come away with this idea that, where's the creativity? If there's a cookbook way of doing science, and this is, you go step 1 through step 6 and repeat, that is so boring. I don't blame students for thinking that that's boring, because it is. And it also leaves little room for creativity and serendipity and error, which are all a huge part of how science works and how science is conducted. So I really encourage you, and this is going to take some practice, chances are good, because I have to correct people all the time, even my colleagues, to ban the. So don't talk about the scientific method. Talk about scientific methods, and don't talk about the scientific process. It's scientific processes, because there really is no one way of doing science, and there's no one way that a scientist looks. Science is something that's happening all around, and the only thing that all science has in common is all science is about understanding the natural world. That's it. Other than that, anything goes. Any person, any way, any how, it's all science, and it's all wonderful. We know that, and we need your students to know that too. So, what's the deal? Why do we need to change students' image of science? So again, I'm repeating myself, but students can't feel that science is a foreign place where they don't belong. They don't look like scientists. They don't think that way in that linear method. That's not for them. That's bad. We can't have students pigeonholing themselves as not a science person. Everyone can apply scientific thinking skills every day. Reading and writing are skills that you pick up, like Anne was talking about other skills. You use reading and writing every day, and math and counting. You use these skills every day, even if you don't become a mathematician or a professor of literature or a writer. And science is the same thing. You use science all the time. My dream would be, if you ask students on that first day of class to draw a scientist, draw themselves. Because whether or not they become a professional scientist, they act the role of scientist at some point every day of their lives, which is, again, awesome. And we just need to make sure that they see that too. And besides, science is important. One of the challenges that teachers have, of course, is connecting material to their students' lives, making it relevant, making it interesting, answering that dreaded question of, when am I ever going to use that, or why does this matter? Well, science is everywhere. It affects how you interact with the world. Science and engineering are responsible for cell phones and equipment and medicine and everything these kids do pretty much every day. And it's a huge part of policy decisions. It's a presidential election year, so you'd think there'd be more science, but underneath some of these policy decisions, there is science, whether or not people are talking about it or not. And science really does affect every aspect of modern life. Everyone, no matter what they end up doing, is a consumer of science and lives in a very scientific world. And so we need to make sure that our students can navigate that world and feel a part of that world. And misconceptions about science, which we're going to talk about today, just a few, as Anne said again, they really are, they form points of weakness is one way of thinking of it. That outside forces, which I know sounds very nefarious, but there are groups with an agenda to keep people in the dark when it comes to the truth about science. And people who are afraid of science and share their fear of science and share their distrust of science and scientists. And we need to make sure that students are prepared, are inoculated against that kind of attack. And that's the end goal. So, what is science? Science is an everyday way of thought. It's a way to understand the natural world. I love this one, using what you know to find out what you don't know, because that's a lot of what happens. Again, mistakes, serendipity, answering a question that you're curious about and kind of going after the answer, that's science. And it really is creative. It involves a tremendous amount of curiosity. But yes, there are rigorous reality checks. It's science. What makes science science is you're constantly testing these ideas against your evidence, which, again, is a strength of science, although, as we'll talk about, some people seize upon that as a weakness, but we know that it's a strength. So the goal for today, we're going to cover we're going to cover 4 misconceptions about science, 4 of many. Again, if you do the assignment, check out the Understanding Science webpage. There's a list of misconceptions, and some of them you probably hadn't thought of, some you're going to recognize right away, but they're all out there. And many of them are reinforced intentionally or unintentionally in the classroom. And the easiest way to think about this is what's chapter 1, unit 1 of every textbook. It's the dreaded "What is Science" chapter. And that often is written in a way that makes you think that that science is something that is very specific. It's something that happens only in science class. There's one way of doing it. And most of that is, as we just covered, not the best way of thinking about things. And so if you're aware of these misconceptions, if you ban I mean, that was sort of a bonus misconception that we got, that I snuck in there. If you're aware of them, then you can make sure they don't take root in your student's mind. So let's get to the first misconception. True or false? Speaking of textbooks, now I have to, as a caveat here, I was a textbook editor for a number of years. I enjoy textbooks. I don't have a beef against textbooks. But here's the question. True or false, these books contain science? And then I put a note, it's a trick question. So on the one hand, of course, they contain science. They are science textbooks. But it's really only half true. So science, the misconception is that science is a collection of facts. The correct way of thinking about it is, yes, that's true. Science is a body of knowledge that includes facts and theories and discoveries and observations, but it is also a way of knowing, a way of discovering that knowledge. And so the problem here, if students get the impression that science is just a bunch of facts that have already been discovered and they're just sitting here in this enormous textbook, what's the point? Why do I need to know things? Why is it important to know the cell theory, which was discovered hundreds of years ago? Like, who cares? I'm not going to do anything with it. Well, of course you are, right? Now, science does rely on some facts, and facts are good. I don't want to give anyone the impression that facts are not important, that you can just focus on the process of doing science. Because facts are good. Facts tell you things. Facts give you knowledge. But that's not all science is. Okay? Science is also that discovery process. And if you don't make sure that your students understand that and understand that other side of the coin, then you're just inviting the what's the point? There's nothing to do. It's just so boring. Who cares? All I have to do is memorize things. This is like the worst class ever. And it can be hard. This is a real challenge for teachers because there is a lot of memorization. There's a lot of vocabulary that you need your students to learn to pass their tests, to succeed and to meet the expectations of your school and your state. There's a lot of terms, and there's a lot of, it can get jargony, and it can get overwhelming at times for your students. And also the labs, the discovery part you might get to do, are often have to be constrained because, for time purposes, for safety purposes. So this is tricky. I'm not suggesting that you can just kind of wave your wands and make all students understand how awesome it is, but there are ways. You can show them videos, you can talk about scientists doing amazing work, and you can relate things like the cell theory or things that seem very static and just a bunch of facts, relate it to cutting edge research that's going on and make sure they understand what the point is, that this is an active area of research, that there are so many questions that are left unanswered, and the reason that you have to learn these basics it's not a means to an end of itself. It's so that you are armed with the skills to go on and start answering some of these really interesting questions in creative ways. So let's go to misconception 2. True or false? Science is a way to find the truth. Okay, so that's false. And this, again, I was alluding to this earlier. This is one that drives me crazy. It'll happen all the time. I'll be listening to a science podcast or you see scientists being interviewed, and the interviewer will say something like, so you proved it, right? So this is just huge. You proved it. And the scientists will go, well, I haven't proven it, but I'm fairly confident. Now, to a student's ears, that is an invitation to be like, what's the point, right? We're used to a world where you prove things. You know the answer. I know this math question. I've answered this math question correctly. This is it. I'm done. It is the correct answer. But science doesn't think in these absolutes. That's not how science works. Valid scientific results don't represent truth. They either represent support for a hypothesis or they detract from the hypothesis. They either refute a hypothesis or support it. Science is never final. It's just not how science is made. It's not how it works. Even though we're pretty darn sure that gravity is true, scientists will never say they've proven gravity. It's just not how it works. So how do you make sure your students understand this as a strength and not a weakness? Well, even though it's never final, that doesn't mean that we're not pretty darn sure. Okay? Science is self-correcting. That's the strength of science. And if at any point, all of a sudden objects aren't falling toward the center of the Earth, but they're bouncing back up and floating well, we've got to go back and reconsider this gravity thing. And that's cool, I think, and hopefully your students will think so too, that you never rest on your laurels in science. You're always on the lookout for new information that will counteract or that will continue to support the ideas that we hold. Now, after a while, we get pretty darn sure, right? And it's important that you, even though you're not going to use the language of it's proven, you can talk about how in evolution, for example, the incredibly rigorous testing that evolution has been subject to for more than a century, it's all pointing in the same way. Evolution, does it occur? Yep. Have you proven it? No, it's not what we do in science, but I have this incredible, vast, overwhelming amount of evidence that tells you that this is how things descend with modification from their ancestors. Same with climate change, same with gravity. It's important not to single out evolution and climate change. Same with, atomic theory. It's all the same. We build evidence. That's what science is in the business of doing. But what's the problem with it? The problem is if your students think that science should be something that you can prove, that it should be something you can prove, then you hear a scientist say, oh, well, I haven't proven it, but I have, this presents new evidence, that strongly suggests that my hypothesis is true. All they'll hear is, nope, I have no idea what I'm talking about. So you have to make sure that students understand this is, again, going back to Emily's lesson, part of the language of science. And it, again, needs to be seen that just because scientists won't say they prove anything, that doesn't mean that they aren't sure. It also doesn't mean that they don't feel very confident in their results. Okay, and that confidence varies. A cutting edge thing that's only been tested once, and this is the first time we're seeing it, probably not as confident as someone who studies the basic premise of evolution. Okay, now this is a quote. Unfortunately, it's unattributed, but it's wonderful, so we put it in anyway. That what science is the best tool we have to make sure we're not fooling ourselves. Okay? This is just how science works. There's no alternative. There's nothing else except for dogma that can tell you with certainty. So you just have to get your students used to this idea that science operates differently from math. Science operates differently. And that's okay. That's actually a good thing. Science can correct itself.
So before we go on to the next misconception, have any questions come in, Minda?
Yes. Hold on one second. Let me see. Let me pull them up really quickly. Stephanie, did you want to respond to the question that you got earlier?
Oh, yeah. Excellent. Yes. So, teachers, experienced teachers have lessons. They work well. Your guys are always rushed. So that I think it was asking basically, I don't really have time to revise my basic intro to science and scientific methods lesson. Are there resources? And there absolutely are. The best place to go is Understanding Science. That's the webpage. Just put it in Google. It'll come right up. And they have a teacher's lounge with links to all kinds of resources, lesson plans, and ideas and ways of bringing this into your classroom. So it'll all be right there. And one of their tips, which is something that I completely agree with, it's now, what is this, February, end of February? So you've also likely gone way past this lesson. And that's okay, because one of the best things you can do is continually show how science works throughout the year. So it's never too late to bring in an example of ongoing science and how science works no matter what unit you're in.
Great. Thanks, Stephanie.
Any other questions, or should we go on?
I think that was it for now.
Okay, misconception 3.
Come on down. Wait, back up. Wait, is that one wrong? Oh, yeah, go to this one. Sorry, I got ahead of myself. Problem and misconception 2. Rewind. So again, back to this idea that science can't prove anything. Here's a further problem. There are always going to be new problems to solve, right? So if you reject science, then because it can't prove anything, so what's the point? You're taking away the most powerful tool that we have to understand what's happening to the world. And this is really no more obvious than when it comes to climate change. Are we 100% absolutely, positive? Have we proven that climate change is happening and here's exactly what's going to happen? No, not how science works. But if we just throw up our hands at that and say, well, forget it, science is useless, we're not going to solve these problems that we know are happening. Okay, so your students are going to grow up and they're going to have to solve the problems. They need to trust science. So you need to make sure that students don't close their ears when they hear, nope, that doesn't prove anything. They need to hear that as a strength, not a weakness, or else we don't stand a chance against some of these big problems. All right, now, misconception number 3. True or false? When the vast majority of scientists in a particular field reach a consensus position, it's because scientists are herd animals. You can tell we've given up a little bit on actually making these answers anything but obvious. So the screen grab here is from a wonderful skit from the Tonight Show, from This Week Tonight with John Oliver. And this is a year or so ago, and he's talking about how you always get this debate on climate change, and the pundits will bring in Mr. Scientist and Mr. Climate Denier as if it's an equal position. There are two sides. I'm going to show one person and one person. That's not how this works, again. So the correction to this misconception, going on to what happened next, John Oliver then brought in 96 scientists, in addition to the one he had, making 97 scientists, and 3 climate deniers, which would actually reveal the proportion of, it would actually reveal the consensus on climate change. And then they all started screaming at each other, and it was very amusing. You should check it out if you haven't seen it already. So the misconception here that scientific ideas are judged by popular vote, and scientists just have to go along with the mentality, is wrong. So when scientists agree on something, that means that their evidence agrees. They're evidence that they both individually been working on and probably come from different sources, are pointing them to the same conclusion. And new and convincing evidence, it'll change minds, of course. Like I said, all of a sudden everything starts floating up. Something weird's happened to gravity. We need to figure this out. But you're going to have to work really hard to get that to work again. So you don't just say, oh, one thing, that's it. It's more, all right, well, let's figure out how this could fit in, how this new information could fit in with what our conclusions had previously been. And this idea that there's equal weight, that because there's one scientist who doesn't think that there's climate change must mean there's two sides to everything, again, that's a very dangerous notion. There are hundreds and hundreds and hundreds and hundreds and hundreds of scientists who have come to the same conclusion about climate change, all from a variety of different ways, interesting, creative methods, and that is important, right? The reason that we can confidently say that there is an overwhelming consensus that climate change is occurring and its main factor, its main cause is anthropogenic or human caused, is because we have an incredible amount of evidence from a hugely diverse number of fields and studies that all come to that conclusion.
And that's so just to reiterate that. Sorry to interrupt you.
No, go for it,
Stephanie. That very messy diagram of how science really works is helpful here, because if, let's say you're a scientist who works on the succession of plants in your local national park. Maybe invasive plants in your national park, or maybe you're dealing with some new pest that has come into your park, and you don't work on climate change directly, but you say to yourself, well, if climate change is happening, what would I expect that to look like in this part of the world that I'm studying? So there you have a hypothesis, you have a question that you need to ask, and then you figure out, well, how would I determine whether climate change is affecting this local environment? And you may look to see whether the range of certain plants or insects is changing over time, that you used to see this butterfly at this part in this part of the park, and now you're only seeing it higher up or further north in the park. You may see that plants are blooming earlier. In fact, they might bloom before their pollinators get there, because the plants are getting their signals from the temperature, and the pollinators are getting their signals from the day length. And when a scientist looks at his or her evidence in her little part of science and finds that, well, it turns out that exactly what you would expect to be happening if climate change is real is happening, then there you have another piece of evidence that is reinforcing that overall consensus. It's not that, the 99th person who does climate models looks at the models and agrees with the previous 98. It's that 99 people from all different areas of science have asked the question, what would climate change look like in my territory? And they all are finding the evidence pointing in one direction.
Yeah, climate change is an incredibly interdisciplinary area of science, and it's really interesting because we ask people, who are the climate scientists? A lot of people they're not trained as climate scientists, but their research in light of what's going on in climate change, they're contributing to the body of evidence in support of climate change. So it is, as Anne said, it's a really interesting field of study, and this idea, which you'll hear, that the reason there's a consensus is because all scientists have to agree, and there's pressure to accept climate change, and that's so they're all just kind of walking in lockstep, is insulting. It's not how science works, and that is to suggest that that's going on just shows complete ignorance on how science works. And speaking of, what's the problem with this misconception? Well, we've covered a lot of it. This is Senator Inhofe, who last winter went to the floor of the United States Senate with some snow that he gathered from outside of the building, and brought it in as proof that climate change was not real. And it got a lot of play, not because it was ridiculous, but because people were saying, oh, yeah, look at that. And you hear this all the time. People who try to debunk established science, though they often complain that they're not, no one's listening to them because it's no one wants to listen to them because they're not scientists themselves, and it's not part of the agenda. But it's not true. If Senator Inhofe wanted to do a study and present his findings, I'm sure climate scientists would be all ears. But the fact that there was snow in Washington, D.C. in the winter is not a piece of evidence that would contradict climate change models. And you'll see this a lot, where people who try to push back against established science, they don't really present their own new evidence. They are seizing on people's ideas, misconstrued ideas of how science works, and basic science, and how science works as a process. So what we need students to do is to be able to look at that and say, that's ridiculous. That's the goal here, so that this doesn't seem convincing. But unfortunately, it convinced a lot of people, and he got a lot of support for this stunt.
So, Stephanie, I have a question. It seems to me that lots and lots of scientists would love to be the scientist that disproves something that everybody thought.
Oh, yeah.
So this sort of lone genius scientist who comes up with something that completely changes the way people think about things, and it does happen sometimes. And
Sure.
Think about the guys who figured out that ulcers were caused by a bacterium instead of by stress. So
Yep.
sometimes the consensus is wrong, and somebody who appears to be an outsider turns out to be right.
Absolutely, and one of my favorite examples, and go back a bit, but the guy who really understood plate tectonics was a meteorologist. He wasn't a geologist, and he just made some observations. So he was like, wait a second, it looks like the continents are moving. And outside voices, and Darwin himself, he wasn't he had some training, but his schooling was a little here and there, so mixed. He didn't step on the Beagle as a naturalist. He stepped on the Beagle as a companion for the captain. And his observations, he was like, wait a second, this doesn't seem to me to jive with some of these ideas that people had about the natural world. Yeah, these outsider voices, they happen, absolutely, and that's what's exciting. But they don't happen very often, is one thing. And often when they do, so they don't happen very often writ large, and then within the times that they do happen, it's often at a much smaller scale than something like Darwin figured out. And in fact, I'm undercutting when I said that. I could kick myself, because there are a lot of people who were thinking about evolution occurring in ways contrary to the prevailing views before Darwin. He just came up with a really great explanation of it. But when they do happen, they're at a smaller scale. So it's not like all of a sudden gravity doesn't exist. It's like, hey, did you notice that this weird thing that we thought happened in this very particular corner of gravity actually works differently? And that still is super exciting to scientists who study gravity. But it didn't overturn the whole thing. But to always be open to being completely overturned, that's great, right? I mean, because that, first of all, keeps you on your toes. You don't sort of sit back and say, well, I got this figured out, what's my next problem? You keep wanting to add to the evidence, which is remarkable. And you never stop. Science doesn't stop. We haven't decided, all right, we got this evolution thing, let's move on. No, we're going to keep trying to get deeper and deeper and deeper and deeper, and we're going to understand more and more and more, and we're always going to be open to the possibility that some long-held understanding could be overturned. But it would get overturned with very good reason, and people would be very excited about it. Unfortunately, there hasn't been a whole lot of evidence that after all, climate change isn't happening. That's not the way things are going.
Well, there's nothing that scientists like more than an argument, and they actually really it's a big part of science to argue with each other about the evidence and the interpretation of the evidence. So if someone comes along with something like plate tectonics or something like the germ theory of ulcers, they better have some really good evidence. And if their evidence is compelling, all of those other scientists are going to go look and see if
Absolutely.
they need to rethink what they're doing, or they need to demonstrate that that person's new idea is incorrect. And you'll see this in the coverage of science all the time. There was a big story a few years ago, someone saying that certain bacteria that live in very polluted waters can use arsenic instead of phosphate in their DNA. And that was an astonishing claim. And it turned out to be wrong. And that's what science does, is they take the, if it's the more extraordinary the claim, the more scientists will jump right in to see whether it's right or wrong. And that's where this misconception of someone like Inhofe coming along and saying, hey, it's snowing outside, what happened to global warming? That when the denialists come up with a semi-plausible argument, scientists will jump in and look at it and say, really? Has that really happened? Are those measurements really wrong? And they'll check it, that's part of what scientists do. So the idea that they just reject it and refuse to listen to it is a real misconception.
And this you're illustrating the remarkable nature of science as being self-correcting. So what you said is true. So if someone comes in and says, hey, everything's floating, gravity must not be true anymore, scientists don't go, oh, okay, thanks, good to know, let's go rewrite everything we know. Absolutely not. They say, wait a second, I got to investigate this myself. And they all jump in and they start investigating it. And you find out, that's how you catch mistakes. That's how you refine your ideas. You don't take anyone's word for it in science, which is wonderful. And this is I think that this can lead to a bit of conflict with teaching, because to an extent, when you're teaching science, you're asking them to sort of take your word for it, because you got to move through the material pretty fast. But you can use illustrations like these ones that Anne has brought up, and there's tons of others, and you can write to us and we'll give you some. And you can use that as a way to get your students to understand that you don't just take someone's word for it, that all of this stuff that you're presenting as facts, and again, facts are important, they're facts for a reason. And if they one day discover something that runs contrary to one of those facts, or that makes a hypothesis not as likely or overturns a long-standing theory, here's what's going to happen. And that's great. It can absolutely happen. But there's, it's self-correcting. And so if they made a mistake, they'll catch that too.
Okay, let's move on to the last misconception. And this goes back to something that we talked about in the very first session, that people's discomfort with evolution is often not based in a real understanding and therefore rejection of the science, but with this misconception, which is that science and religion are incompatible. So this is, especially in some communities, you're going to have a lot of students who have grown up with this idea that science is somehow against their religion, that they can't maintain their faith and be a scientist. So this is absolutely not true just based on the empirical evidence, because most scientists in the United States consider themselves to be people of faith, and most religions have no problem with the processes and the methods and the conclusions of science. Even Darwin said that he did not see a conflict between accepting all of the evidence for evolution and having confidence that that was how the diversity of life had occurred, and still believing in God. So this is something that you're really going to want to get out in the open with your students, and have them look at the evidence that for all of the scientists who are religious and all of the religions that accept science. Pictured here is Ken Miller, who's a professor of evolutionary biology at Brown University. So Stephanie, I should play this, right?
If you can, yeah.
Let's see.
The gentleman said, thank you for making clear to be an evolutionist without saying there's no God. There's another guy who made that clear too, and that was Charles Darwin. And Darwin got many letters saying, why don't you come out against God? Why don't you attack religion? You've done away with the need for God. And in one letter, and I can almost quote it exactly, Darwin wrote back and he said to his correspondent who had asked him to take a position against religion, he said, I do not doubt for a moment that a person can be, Darwin's words, an ardent theist and an evolutionist at the same time. And he noted, my most prominent scientific colleague and supporter in the United States, the Harvard botanist Asa Grant, is in fact a devout Presbyterian and has written extensively on what he regarded as the harmony between science and religion. So Darwin said, even though I'm not a religious person, other evolutionists like Professor Gray are, and you should take your cue from that. So thank you, but I'm in a long tradition in that respect.
Okay, so there's a discussion of scientists in the past recognizing that science and religion could be compatible, and that continues to be true. Oh, how do I get? Here we go.
Nope. There you go.
This is a picture of our current Pope, who's been very clear about both evolution and climate change, that he doesn't see any incompatibility between being a faithful Catholic and accepting these areas of science. The current director of the National Institutes of Health, Francis Collins, is not only a Christian, but an evangelical Christian. And most religious faiths, we have a list of them at the NCSE website. You can go search for Voices for Evolution. Most denominations have formally said that they don't have a problem with this. And so some of your students may really struggle with whether they can reconcile their faith and science. You should at least be able to point to them a very, very large number of people who don't see that conflict. Of course, that's a decision that they would have to make themselves, but they should at least have this corrective that it's not a given that scientists are anti-religious and that you can't be a good Christian and be a good scientist. So how do you deal with this when these misconceptions arise, or even perhaps more importantly, when they don't overtly arise, but you just want to make sure that that you're giving your students a chance to air them? So we recommend that now that you know about them, that you listen for students saying things that might indicate that they have some of these misconceptions. And we'd be happy to have you give examples. That would be a great way for all of us to learn more about this. If you have any examples of students saying things that you recognized, oh, that's rooted in really not understanding how science works. And then it's important not to just shut them down and move on, but to acknowledge that these misconceptions exist and to ask your students questions that help them articulate what they're thinking about science, which should sort of flush out some of these ideas that are based in a misconception of how science works. Do we have any questions that have come in, Minda?
Yeah. I'm sorry. Go ahead.
Oh, okay. I'll ask this one really quickly. So one here is, my students often come in talking about new health information about how some foods are good or bad for you and ask me what the point of science is. What should I tell them? I think the typical one we always hear about is eggs, right? Eggs were bad, now they're good. So science is stupid. And help us out with this one.
Yeah, so that's a great misconception, a sign that this student has a real misconception about science. And it's rooted in this idea that science should be uncovering truth, and therefore if one scientist says eggs are good for you, that's the truth, and then if another scientist says eggs are bad for you, well, that's the truth, and now you've got conflicting truths. And nutrition research is absolutely the bane of all of us who would like students to find science a powerful tool, because this happens all the time in nutrition research, that you get what look to be incompatible results. And but it's a great teaching opportunity because you can actually have your students go and look at those studies and see and ask them, well, what did they actually do
Right.
in this study? How big was the group of people that they used to come to that conclusion? How long did they follow those people? How did they know how many eggs those people were eating? And how did they come to their conclusion? Because if you dig into 3 or 4 studies of eggs or caffeine or sugar or any other single food, your students will find out really quickly that those studies were quite different. And so it's not surprising that they got different answers. So, the headline writer may summarize it as eggs are good or eggs are bad, but the scientists and the scientific studies that underlie those articles usually are considerably more subtle than that. And then the next teaching moment is to say, well, what kind of study would you design to figure this out if that's important to you? If you are, if that's a big deal to you to know whether it's okay to eat eggs or not, now that you've seen how different scientists have studied it, how might you answer the question to your own satisfaction? That's a great way to get the students thinking about how scientists actually go about asking those questions.
And another thing that will, by actually sending them to the research, which is such a good idea, that they'll find is that nowhere in that paper did the scientists say, I have proven that eggs are good for you. They'll say that given what they, given this particular research and these, parameters that they set out in this study, this is the conclusion they're coming to. But they're open. Science, they're not trying to prove yes or no. They're open to additional information. And so a different study, like Anne said, will have different parameters and will look at things a little bit differently, and it might come to a different conclusion. But all these things taken together are going to help get closer to the actual answer, right? Which is actually going to be messy. And this is one thing, the reason this comes up all the time in health studies is because humans are messy. We're not neat little controlled experiments. There's more variables than can be controlled. And you do try to control them anyway. You can't, there's only so much you can do. And this is it's exciting. That's why health is such an exciting field, because you can look at it in so many different ways. And all of it together is going to help improve our understanding of eggs in this example.
So that's what we've got on these very basic misconceptions about science that I think a lot of your students are going to be coming into the classroom with. I think if you spend some time at that Understanding Science website, there's a whole section on misconceptions. I know that even though I was a practicing scientist for many years, I had a little shock of recognition with some of them that, oh, I guess that's kind of how I thought about science, and it's not, and now I see why that's a dangerous impression to give. So what we hope by having your antennae up and listening for signs that some of these misconceptions are rooted in your kids' minds, that what we're hoping is that over the course of a year, as you again and again kind of bring these misconceptions out into the light and help the students see why that's not how science works, that when they do leave your classroom, they will be able to really think like a scientist and to see themselves thinking scientifically, to recognize that they can ask good questions and they can figure out how a scientist would go about getting answers to those questions. And if they have that, then it's going to be much harder for those students to be swayed by some crazy claim, in the late night infomercials, or in a politician who says, I reject this entire area of science based on a snowball, or a neighbor or a friend who says, I'm not going to get my child vaccinated because I think it's dangerous. They are going to have learned over time and have it reinforced again and again and again that science has these very rigorous standards, and it's a great way to think through complicated questions about the world that we live in so that we make better decisions. So any
Well,
questions at the end?
I think that's it. Thank you guys so much. I think maybe we should point out that the next workshop is on Wednesday, and Stephanie and myself are going to be doing another series on misconceptions with a little bit more of a focus on specifics relating to climate change and evolution. And then the last session will build off of a lot of the things that you guys were talking about today. I'm going to be talking about actual practical in the classroom tools that you can use when these kinds of issues come up. So I hope everyone tunes in for those ones as well. Thank you guys.
Thank you.
Look forward to getting your questions. Send them in.
Okay.